So in this lecture, we are going to talk about how branch and bound works inside the setup of simplex at the dictionary level. Our overall goal is thus far, we've been looking at using the LP solver as a black box. Okay, now this is not too bad, but it redoes a lot of work, which we hope that we can save. And in this lecture, we are going to talk about how can we fold branch and bound better into a dictionary setup. We'll see that we can reuse the final dictionary. Okay, so we can reuse the final dictionary that we obtain at one node by solving the LP relaxation to consider the LP relaxation of the child nodes. Okay, and the key goal is how do I reuse the final dictionary, number one. Number two, how do I avoid solving simplex, the initialization phase at least, how do I avoid doing that one more time, okay, unnecessarily. All right. So what's the view from the angle of a dictionary doing simplex? Okay, so here imagine the situation where you have solved for a branch and bound node and you have solved the LP relaxation. You decide that the solution B for the basic variables is fractional or has fractional entries, and therefore I would like to now select a branch variable and do branching. Okay, so I select a branch variable, let's say xj is selected, and let me imagine one of the children here, xj less than equal to the floor of sj, which is the value of the branch variable right here. Okay, this is clear. Then we get a new dictionary. Okay, so we can take this original final dictionary from here. Instead of starting from fresh with this new constraint added, we will take this dictionary D and come up with a new dictionary D prime, where we will add an extra row to the dictionary corresponding to this constraint. So we'll add an extra slack variable W. Okay, I'm misusing the notation slightly, but just to show that we add an extra slack variable W for child 1, and we add a row corresponding to this constraint translated into this basis number 2. Okay, I hope this is clear. This is a very important point, and if you understood this, then we can think about how we can now start the simplex from this dictionary D prime instead of starting it all the way from scratch. I hope that's clear. So the first thing I will note is that this dictionary D prime is going to be infeasible, and in fact I can tell you that the constant corresponding to this W is going to be negative. Okay, I can tell you that, I can give it to you in writing. Why is that? All right, let's take a look. Okay, so here's how it works. So here is the solution that's represented by the original dictionary D, which is the optimal point of the LP relaxation shown in blue. Okay, it's shown in blue right here. I'm outlining it. Okay, and the solution represented by the dictionary D is right here. Now, let's imagine what happens to dictionary D prime. So imagine here is dictionary D prime. Okay, the solution for D prime is the same over the variables xb and xn. So over the variables xb and xn, it remains the same. We add an extra dimension W on which we add a new solution here. Okay, so that's going to be D prime. So if you look at D prime also in the space of the original problem variables, then you see that D prime and D are the same point. Okay, in the dimensions of the original problem variables, they are the same point. And therefore, if you now look at what branch and bound does, it makes sure that this solution, the LP relaxation feasible solution, is no longer feasible in either of these two branches. The first branch excludes this, the second branch also excludes this. And therefore, we have a simple geometric proof that this dictionary will be infeasible. Very simple geometric proof. We can make it algebraic, but there is no need. We have done geometry, we can use it. So here is our paycheck for understanding the geometry. Very good. So let us now take an example. Here is an example. Okay, I have written this example out as I would write in an ample file, and that's by choice. And here I have variables x1, x2, x3 that are the original problem variables. I'm saying x1 is greater than equal to 0, x2 greater than equal to x3 greater than equal to 0. So that puts my problem in a standard form. But I also say they are less than equal to 10, less than equal to 10, and I have 3 constraints shown right here. So the entire problem is actually in the standard form. It's also a maximization problem. Okay, now I can take this problem and I can add slack variables. Okay, and one thing I haven't shown here is that x1, x2, x3 are integers. Okay, so this is an example ILP, even though the ample problem that I've shown here is that of the LP relaxation. Now I can add slack variables x4, x5, x6 for these 3 constraints, less than equal to 10, less than equal to 10, less than equal to 10. So I get 10 minus x1, 10 minus x2, and 10 minus x3. Okay, so going back, we have x7, x8, x9 corresponding to c1, c2, c3. And this is just standard. I've just added it, and I've skipped the various steps in doing so. Now, let me go ahead and solve this using simplex and write down the final dictionary that I get. And here is the final dictionary, okay? And as you can see, x1 and x2 are the original problem variables. So the value of x1 is 5.67, x2 is 1.33, and x3, which is also an original problem variable, has a value 0. Okay, now with these three, you can clearly see that the solution is fractional. So I can choose one of these three, but in fact, it turns out that the way I have set it up, the slack variables are also integers. And I will talk more about this later on when I talk about cutting plane methods. So in this problem, I can do x4 or x5 as well as one of my constraints for branch and bound. I can include the slack variables as part of my branch and bound strategy. But here, let me just proceed by choosing x1 as the branch variable. Okay, so the constraint that needs to be added is x1 greater than equal to 6. That's one of the branch constraints, the other being x1 less than equal to 5. Now, x1 less than equal to greater than equal to 6, if we approach this process naively, and I'll talk about a more intelligent way of doing this later on, we get a slack variable x10, which is minus 6 plus x1. Okay, so we can now start to insert the slack variable into the dictionary, and we do so by adding a new row for x10. And then you have to now, previously x10 was minus 6 plus x1, but x1 itself is basic. So you have to express it in terms of x8, x9, and x3, and we have done so right here. It's a very simple substitution which we have done. And as you can imagine, here we have the dictionary being infeasible. Okay, and therefore the question is, do we go back to the initialization phase simplex and reinitialize this problem to make this dictionary feasible? And the answer is we could do that, but my guess is we will be wasting a lot of work if we did that. Instead, there's a simpler answer, which is notice that even though this dictionary is primal infeasible, it also has all zero or negative coefficients in the objective row. Therefore, if you make the dual dictionary, it turns out to be dual feasible, but not dual final. And the reason it's not dual final is because this minus 0.333 goes into the dual dictionary in the objective row and becomes plus 0.333 and becomes an entering variable. So this dictionary is not dual final, okay, but it's dual feasible. So therefore, we can avoid the initialization phase if we remember our lessons learned from the complement dual dictionary, which is we can start with the final dictionary of the parent node. We add the branch constraint. Okay, so far we have seen this. We get to a child node and we add a new row, which we will talk about how to avoid adding a new row. But the resulting dictionary we have seen is primal infeasible but dual feasible. Okay, so what do we do with this dictionary? So we already talked about how to avoid initialization phase, and to avoid it, let us take the dual complement dictionary, which will be feasible because we started off with the final dictionary here, so it will be feasible, but non-final because it's primal infeasible. This is a very key fact, and I hope you understood this fact, otherwise it's very hard to proceed. Okay, so then what we get is we can now just directly do the optimization phase, but not on the primal, on the dual dictionaries. Okay, and those of you who have taken care to read more than what I have taught, you will also know that this is called dual simplex. Okay, so we do the optimization phase on the dual dictionary and we get to a final dual dictionary that's also by strong duality translates into a final feasible primal dictionary. Okay, that's how we avoid doing the initialization phase and just do one phase, which is the optimization phase. Okay, and therefore you get the LP relaxation solved for the child node and the answer for the child node. Okay, to summarize, add the new row, you get primal infeasible but dual feasible. Complement the dictionary, you get the dual complement dictionary. It's feasible but non-final, and therefore you take this final dual dictionary, you do the optimization phase on this dictionary, starting from this dictionary because it's feasible, you can do that, but do it on the dual dictionaries, get to the final dual dictionary, and then retranspose, rearrange it to get the final primal dictionary, and the LP relaxation has been solved for the child node. I'm very happy presenting this because this is the payoff we get for studying the dual, for taking the time to study dual that we did in week 4 and week 5. And this is the payoff that we get for being so diligent in studying the dual. We can now start to do things very efficiently. But unfortunately, we are not quite there yet. One of the problems here is we need to add a new row to the dictionary, and as you keep doing branch and bound, you're going to start accumulating a large number of new rows. But then what are these rows like? Okay, so one of the things you will note is that these rows are always branch constraints. So if you go back, the row that you add is always going to arise from a constraint of the form variable greater than equal to constant or variable less than equal to constant. Those are the kinds of branch constraints we obtain in branch and bound. Okay, so if that is true, then how do we proceed? Okay, the way we proceed is to construct a new form of a dictionary called a general form dictionary. Okay, I will talk about this in the supplementary videos if we have the time next week. But to understand general form dictionaries, just remember that we give special treatments to bounds on variables. The bounds on variables L less than equal to X less than equal to U are maintained specially on the side in the dictionary structure itself. And they are not treated as general constraints, they are treated on the side as special constraints. And simplex algorithm is modified in two ways. The dictionary structure is modified to track these bounds, so we have extra information on these bounds. And pivoting is modified to take into account these bounds when we pivot. Okay, it's not difficult modifications, but it's still tedious, and we have to talk about the duality theory for these dictionaries, the dual dictionary, the initialization. So there is some work to be redone, and I'm not doing it as part of the main sequence of this course, but there are plenty of references on general form simplex, and I hope if you are really serious about implementing this, we will go look at general form simplex and then revisit branch and bound. Okay. Therefore, the way branch and bound works with the general form is exactly the same as I showed you previously, except that the question of adding a new row never arises. What we simply do is we maintain the variable bounds and we simply update the variable bounds. So the dictionary structure does not grow in size by adding new rows or adding new columns. I hope that's clear. Okay, and everything else proceeds as before, except that we modify the algorithms to do the dual simplex on the general form dictionary, the primal on the general form dictionary, and so on, which is a little bit more tedious, and I'm not going into it right now because it's a little bit off the mainstream of this class. Okay, so I hope this is clear, and this idea will be revisited when we again get to the process of doing cutting plane algorithms, which is going to be the title of my next lecture. I will see you there. Thank you.